Hi everyone, what's up? Today we're going to be doing some thermodynamics and we're going to be looking at chapter 19, which deals with temperature, thermal expansion and ideal gases. After the section you should be able to state the zeroth law of thermodynamics and understand what it's saying and how to apply it. We should be able to define what Kelvin is and what a mole is. We should be able to convert temperature between different scales, so from degrees Celsius to Fahrenheit to Kelvin. Specifically working in Kelvin is important. We should be able to define or obtain linear and volume coefficients of expansion. Then we're going to conclude by looking at the ideal gas law, and we're going to look at different formulations of this ideal gas law. And of course, as with all the chapters, very important is to be able to solve problems using the above concepts. What do we mean by the study of thermodynamics? Well, this involves situations in which the temperature or the state, be it solid, liquid or gas, of a system changes due to energy transfer in the system. So this could mean that we adding energy to a system or removing energy from a system, and this is causing the temperature of the system to change, or maybe it's causing some change in states. Maybe it's causing water to boil and change from liquid to solid. Thermodynamics is very successful in explaining the bulk properties of matter and the correlation between these properties and the mechanics of atoms and molecules. So what they're referring to here is by bulk properties of matter. They say perhaps you pick up your bra iron which has been in the fire and you feel that's very hot. Then thermodynamics is able to explain that bulk property, the fact that it feels hot, by relating that to what's happening at atomic level with the atoms and the molecules in your bra iron. And this helps us to answer some interesting questions, like how is a fridge able to cool its contents? What transformations will occur at a power plant to produce energy? What processes occur in a car engine? All of these types of questions can be answered using thermodynamics. Looking into thermodynamics in more detail then, we often associate the concept of temperature with how hot or how cold an object feels when we touch it. This is to say that the idea of temperature is something very intuitive. Even a young child will know not to touch the stove because they will be burnt. And this second sentence refers to your skin measures the rate of energy transfer between something hot that you touch and your body. But what we actually need is to move away from an intuitive understanding of what hot and cold is, and we need to define a more reliable and reproducible method. So we need to come up with a rigorous way of defining what relative hotness or coldness is. Two objects at different initial temperatures eventually reach some intermediate temperature when placed in contact with each other. By intermediate, they mean some temperature between the temperature of the hot object and that of the cold object. For example, when hot water and cold water are mixed in your bathtub, then energy transfer takes place from the hot water to the cold water, and the final temperature of the mixture is somewhere between the initial hot and the cold temperatures. Two objects when we speak about thermal contact, we're speaking about two objects on thermal contact with each other if energy can be exchanged between them by these processes due to a temperature difference. So when we refer to two objects being in physical contact, we mean that they're actually touching one another, but thermal contact is something different. We can have thermal contact so long as energy can be transferred from one object to another object. So that means that they don't necessarily need to be touching. because the energy transfer can happen through the air, right, through a gap between the two objects. Another important concept is thermal equilibrium. Thermal equilibrium is a situation in which two objects would not exchange energy by heat or electromagnetic radiation if they were placed in thermal contact. So we look now at the zeroth law of thermodynamics, and the zeroth law states if objects A and B are separately in thermal equilibrium with a third object C, then A and B are in thermal equilibrium with each other. Remember what that word thermal equilibrium means. It means that there will be no energy exchange between the two objects. So here we have object A and object B, and we also have object C, which in this case is a thermometer, which is reading the temperature. So object A is in thermal equilibrium with object C, and object B is in thermal equilibrium with object C, and this means that A and B are in thermal equilibrium with each other. No energy will be exchanged between A and B when they are placed in thermal contact with each other. It's quite interesting that's the laws that we have a zeroth law. So in total there are 4 laws of thermodynamics. There's a zeroth, a first, a second, and a third. And what actually happened is people first made, the first, second laws. They were working on those, and then they realized that, in order for us to rigorously define things, we actually need to have a law before the first law. But since the first law had already been made, they decided that, we need to call this the zeroth law. So we look now at temperature scales, and in everyday life, where one temperature scale we're very familiar with is the degrees Celsius temperature scale, which we use in our country. Overseas, people make use of the Fahrenheit scale, and this shows the conversion between Fahrenheit and degrees Celsius. In terms of scientific work, a very important temperature scale is called the Kelvin scale. And you can read through this box yourself and see how it's defined. But very important for us is to be able to convert between the two scales and between degrees Celsius and degrees Kelvin. And you can see there's a factor of 273.15 difference between the temperature in degrees Celsius and the temperature in Kelvin. How this came about is people did experiments where they had some different gases in a container. Maybe they had 3 gases. For example, in one container they had oxygen, in another container they had nitrogen, and in another container they had hydrogen. And what they did is they cooled these gases, and they measured the pressure. And what they found is when they got to a temperature of 0 degrees Celsius, not all of the gases had a 0 pressure. You can see they all had different values of pressure at 0 degrees Celsius. So they wondered at what temperature would all of the gases have exactly 0 pressure. And they extrapolated this, each of these lines backwards, and they found that they intersect at this point on the x-axis at a temperature in degrees Celsius of 273.15. That's this point here. So we refer to 273.15 degrees Celsius as the absolute 0 temperature, and this corresponds to 0 degrees Kelvin. So this gives you a little bit of an explanation of where this equation for converting between degrees Celsius and degrees Kelvin comes from. Let's have a look at 2 examples. In the first example, 2 objects with different sizes, masses, and temperatures are placed in thermal contact. In which direction does energy travel? Does it travel A, energy travels from the large object to the smaller object? B, energy travels from the object with more mass to that with less mass? Or C, does energy travel from the object at a higher temperature to the object with a lower temperature. So here I've made a drawing of what might happen. I've drawn two objects in contact with one another. We have, I've drawn them in physical contact, but the important thing is that they're also in thermal contact. So thermal contact means that energy transfer can happen between the boundary, and no specific information is provided about their temperature. We are told that their temperatures are different, but we're not told which one is at a higher temperature. What we need to realize with this problem is, as time goes by, the two objects will reach thermal equilibrium. And thermal equilibrium means we'll no longer have a transfer of energy. And once thermal equilibrium is reached, the two objects will be at the same temperature. So for the two objects to reach thermal equilibrium and to be at the same temperature at the end, this means that energy must travel from the object with higher temperature to the object with lower temperature, and the solution is C. In the second problem, we asked you consider the following pairs of materials. Which pair represents two materials, one which is twice as hot as the other? And then we're given a number of different pairs. For example, boiling water at 100 degrees Celsius and a glass of water at 50 degrees Celsius. So what we need to remember is that even though in our country we work with degrees Celsius, in other countries they might be working with degrees Fahrenheit. And then this would mean that we would end up in an argument about the different units. So what we would like to do is convert the different cases to SI units, and we're going to be working in Kelvin. So if we convert each of these to Kelvin, for case A we have boiling water at 100 degrees Celsius. If we convert that to Kelvin, we do that by adding 273.15 to 100, gives us that temperature. If we convert 50 degrees Celsius to Kelvin, we get this. And when we compare the temperatures in Kelvin, we can see that these don't differ by a factor of 2. The second case, we convert the temperature minus 50 degrees Celsius to Kelvin, and we convert 100 degrees Celsius to Kelvin, and we do similar for case C. And when we come to case C, we actually notice that the results differ by a factor of 2. If you take 253.15 and you multiply it by 2, then you get 506, more or less 506.15. It's more or less a factor of 2. So the answer is C. So the important point for this question is that we need to work with the temperature in the SI units of Kelvin and not in degrees Celsius, and then make the comparison. We find that as temperature changes, things tend to either expand or contract. As things get hotter, a material will expand, and as it gets colder, it will contract. And here too, very practical everyday engineering examples of that. When people build roads, they need to leave these gaps in the road, or joints that allow for expansion and contraction on hot days. Let's see, when joints, without these joints to separate sections of roadways on bridges, the surfaces would buckle due to the thermal expansions on very hot days, or they would contract and crack on very cold days. Another example is thermal expansion joints in walls. The long vertical joint is filled with a soft material that allows the wall to expand and contract as the temperature of the brick changes. So this is like a spongy material that as the bricks expand and contract, this wall won't become damaged or cracked. If we look at what's happening mathematically, we can have the case where we're looking at an iron bar, and then what's going to happen when the temperature of the bar changes. So if we have just a bar, then we're interested in the length, and how will the length change, right? And then we will use this expression. The change in length is equal to the initial length times the thermal expansion coefficient, the average coefficient of linear expansion, alpha, multiplied by the change in temperature. Similarly, we might have a cube, or we might have a sphere, and in this case, when the sphere expands or contracts, the volume of the sphere is going to change. So then we would use an average coefficient of volume expansion, and the equation is similar, and the change in volume will be equal to this constant multiplied by the initial volume multiplied by the change in temperature. Here are some examples of the two coefficients alpha and beta for different materials. We can see we have aluminium, brass, bronze, so forth, steel. Here we have the average linear coefficient. This is alpha, and note the units of this. This is given in per degree Celsius, and here we have the coefficient beta, the volume expansion, as listed. There are two neat applications that take place, and the one interesting application has to do with us heating a washer, right? So we have some material, and then this is heated by means of a flame, and what actually happens, there's an interesting question, is what happens to the size of the hole in the middle when you heat this material. And the answer to that is, as the washer is heated, all the dimensions, including the hole, the radius of the hole, increase. So the hole gets slightly bigger as well. And so the washer behaves the same way as if it were, just a circular plate filled with the material. The second neat application is where we use bimetallic strips to make a sort of a temperature switch. So the word bimetallic means that in the switch we're making, it has two different kinds of metals, and it's going to be a temperature switch. So when the temperature changes, the switch is either going to be open or closed. We can take a look at how that looks. So if you have a look here, we have two materials at room temperature, and they're glued to one another, right? They have steel and they have brass. They're glued together to make this switch. When the temperature increases, you can see what happens is this surface bends. And this happens because they have different linear expansion coefficients. If you look what happens, we've gone to higher temperature. The length of the brass is now longer than the length of the steel. And the reason for that is brass has a higher linear expansion coefficient than steel. Let's go have a look to confirm that statement. Let's check. The linear expansion coefficient of brass, that is 19 times 10 to the minus 6, and that is higher than that of steel, which is 11 times 10 to the minus 6. So because the expansion coefficient of brass is higher than that of steel, you can see that the length of the brass is now longer than that in the length of the steel, and as a result of this we get this warping, or this buckling of the surface. It's no longer straight, right? So we can incorporate this into a mechanism of a switch, where at 0 degrees Celsius the switch will be closed. Here it's closed, but then suddenly when the temperature, or as the temperature increases to 30 degrees Celsius, we have this change in the expansion of the two materials, and this causes the switch to open as the shape of this changes. Here's two questions to test us. If you're asked to make a very sensitive thermometer, which of the following working liquids would you choose in the thermometer? Would you choose A, mercury, B, alcohol, C, gasoline, or D, glycerine. So how the thermometer is going to work is you're going to have some sort of column, and what you're going to do is you're going to fill it with the liquid, right? And then you're going to have a scale on the side. And as the temperature changes, what will happen is the volume of the liquid will change, and it will rise or it will fall. So if you want to have a very sensitive thermometer, then what you need is a liquid that changes a lot with temperature. So that's to say that even if the temperature changes by a very small amount, it will still the volume will still change, and you'll still be able to notice that. So we actually want then a liquid who has the highest possible beta value, the highest possible volume expansion coefficient. So I've listed it here for the 3 different materials, and you can see that C, gasoline, actually has the highest value at a 9.6 times 10 to the minus 4. So the answer to this question is C. If you think of everyday thermometers, they're actually filled with mercury. So you might ask, well, why aren't they filled with gasoline? Why aren't they filled with petrol if the answer is C? And of course, comes down to practicality, because how safe would it be if you had thermometers full of petrol that can easily catch fire? That wouldn't be very safe, right? The second question we can look at is 2 spheres are made out of the same metal and they have the same radius, but one is hollow and the other is solid. The spheres are taken through the same temperature increase. Which sphere expands more? Is it A, the solid sphere expands more, B, the hollow sphere expands more, or C, they expand the same amount, D, not enough information to say? The solution to this problem is that in fact both spheres will expand by the same amount, so that's C. And the reason for this is exactly the same as the explanation given by that for the rings on the previous slide. If you think about it, a hollow sphere is actually the equivalent, 3D equivalent of a ring, and the sort of solid sphere would be the 3D equivalent of a complete disk. The third question we can look at is a segment of railroad steel track has a length of 30 meters when the temperature is 0 degrees Celsius. What is the length when the temperature is increased to 40 degrees Celsius? Well, from our intuition, we know that if the temperature increases, then the length is also going to increase. But if we look at the calculation for exactly how much it's going to increase by, I have a diagram here. We have the length of the steel. It's initially got length L0, you could also call it Li. And this is 30 meters at 0 degrees Celsius. Then when the temperature increases, it expands by some amount, delta L. So the new length is going to be the original length plus the amounts that it expands by. As we discussed on the previous slide, we can use the linear expansion coefficient, and we can then calculate according to this extra term what the expansion will be. And the expansion coefficient is 11 times 10 to the minus 6 per degree Celsius times 30. That's the initial length times the difference in temperature in degrees Celsius. And then the solution we get is 30.013 meters. You may have noticed that in solving this problem, I worked in degrees Celsius and not in degrees Kelvin. The reason for that is because the linear coefficient of expansion that I used was given in per degrees Celsius. Having said that, whenever you have a change in temperature, a delta T, you can either use Kelvin or degrees Celsius, because if the temperature changes by, say, 5 degrees Celsius, it also changes by 5 degrees Kelvin. So what we look at now is ideal gas, and in working with ideal gas, an important concept that we're going to use is the mole. And much of this work is something that you would have already covered in school. A mole is the amount of substance that contains exactly this number of particles. Perhaps the particles could be atoms or molecules or electrons. When you think of a mole, it's useful to think of, a dozen. When we're speaking about eggs, we often refer to a dozen eggs. And then we know that that's 12 eggs, or perhaps we would like to speak about half a dozen eggs. That's 6 eggs. So in a way, the concept of a mole is in a way similar to that of a dozen. Instead of having 12, it has this number of particles. So if we say we have a mole of hydrogen gas atoms, then we have this number of hydrogen gas atoms. We also, this number then is referred to as Avogadro's number. Often it might be that we have a specific mass of atoms and or mass of material, and we would like to know how many moles it contains. And the way we do that is by making use of this expression. The number of moles N of a substance is related to its mass through the expression the number of moles is equal to the mass that we have divided by the molecular mass. And if we would like to know what the molecular mass is, we can go look on the periodic table, and it's given by the number as shown. For helium, this is the molecular mass. So the molecular mass means that 1 mole of the substance would have this mass, and we can use this equation to find out how many moles of the substance we have. Returning then to the ideal gas law, suppose an ideal gas is confined to a cylindrical container whose volume can be varied by means of a movable piston. If the cylinder does not leak, so the mass of the gas or the number of moles that are in here will remain constant. And then we have the following equation applying. The pressure of the gas times the volume of the gas is equal to the number of moles that we have times R times the temperature. R is what's called the universal gas constant, and it's given by this value here. We need to take a careful look at the units. R has units of joules per mole per Kelvin. And then this means that the temperature that we use in the equation needs to be in Kelvin, right? The volume occupied by 1 mole of any gas at atmospheric pressure is given at 0 degrees Celsius or 273 Kelvin is this volume. You can check this for yourself. You can verify this by substituting the values in the equation and solving for volume. Remember, you know what atmospheric pressure is. Looking more at this expression, this expression, it was found out, it was discovered by 2 different people. It was discovered by Boyle and by Gay-Lussac. And they have two slightly different ways of formulating the same equation, formulating the same rule. Gay-Lussac's version says that the pressure of a given amount of gas held at a constant volume is directly proportional to the Kelvin temperature. So the pressure is directly proportional to the temperature, right? Pressure is proportional to the temperature. For a given amount of gas, that's for a fixed N, held at a constant volume, it means we aren't going to change V. In Boyle's formulation, he says that the pressure of a given mass of an ideal gas is inversely proportional to the volume at a constant temperature. So he's saying that the temperature needs to be constant and the pressure is inversely proportional to the volume, we can see that by taking V to the other side of the equation, that then it will become 1 over V, and we'll have the pressure is equal to 1 over V. So Boyles' law speaks about the relationship between pressure and volume when the number of moles and the temperature is constant. Gay-Lussac's law speaks about the relationship between pressure and temperature when the volume and the number of moles is constant. You'll note that the shape of the graph we get is given by a hyperbola if we plot pressure versus volume. We've already seen that we have a quantity, the universal gas constant capital R, and now we're going to rewrite that gas constant capital R in terms of something called the Boltzmann Constant, K subscript B. Let's see how to do that. The ideal gas law is often expressed in terms of the total number of molecules, N. Because the number of moles, small n, is the ratio of the total number of molecules to Avogadro's number, we can rewrite the gas equation. So we're rewriting this little n, the number of moles, in terms of the number of molecules divided by Avogadro's number. And then what we can do is we can take this A and we can write it as R over, we can take this NA and we can associate it with a capital R, and then that gives us N is equal to KBT, where now we have KB is the Boltzmann constant, and it's given by the R divided by NA, which is Avogadro's number. You can calculate for yourself. This constant has value of 1.38 times 10 to the minus 23 joules per Kelvin. We know that when we open a bottle of champagne, if it's shaken and opened, then liquid spews out the opening, it squirts out, right? And a common misconception is that the pressure inside the bottle increases as a result of us shaking the bottle. This in fact isn't the case, and I'd like you to read through this interesting explanation as to why this is a misconception. We conclude this chapter by looking at an example. A spray can containing a propellant at twice atmospheric pressure, that's of course this, and having a volume of 125 cubic centimeters, is at 22 degrees Celsius. It is then tossed into an open fire. When the temperature of the gas in the can reaches 195 degrees Celsius, what is the pressure inside the can? Assume any change in the volume of the can is negligible. Of course, this is a very dangerous thing to do, throwing cans into fire, so it isn't something you should try. But nonetheless, we're given that we have a container and it's at a temperature of 22 degrees Celsius. We're going to be making use of our law. So in this law, we need to always make sure that the temperature is in degrees Kelvin. So I've converted that to degrees Kelvin. We're given that initially the can has pressure twice that atmospheric pressure. It's in pascals, SI units fine, and it has this volume. Then we're told once it's thrown into the fire, the temperature is 195 degrees Celsius. We need to have that in Kelvin. And we're told that the volume remains the same. So this means that the pressure really is building up because the gas is being heated and the volume staying the same. So the pressure is building up and in fact could explode at any time, which is why you shouldn't try it. Well, you know, this gas law, it applies for both cases. If this is case 1, we have P1V1 is equal to nRT1. If this is case 2, we have P2V2 is equal to nRT2. We can rearrange, and then you can see that P1V1 over T1 depends on nR, and similarly for P2V2 over T2 is also equal to nR. So then this means that these two sides, the two left-hand sides of the equation are equal to one another because they're both equal to nr. And this is an equation that you're probably already familiar with, having used it in school. So we asked to calculate what P2 is, what we can simply then rearrange, and we get this expression, and then we can make use of the relevant volumes and temperatures, and we can conclude by calculating that pressure 2 is 320 kilopascals. So then this concludes this chapter when we dealt with temperature, thermal expansion. We had linear expansion and volume expansion, and then we also had ideal gases, where we used the ideal gas law to solve different problems.